Well, good afternoon, good morning, everyone, and welcome to another exciting Exploring by the Seat of Your Pants broadcast. If you're joining us for the first time, which so many of you are today, we are all about bringing conservation, adventure, and science into classrooms around the world. And today we have so many of you joining, over 500 kids from California to me in Newfoundland. We've got kids in Alberta all the way to Florida. So we are crisscrossing the continent today with tons of excited kids. And I want to say a big thank you for joining us as we continue to showcase the coolest scientists and explorers on planet Earth. Now, this program, like everything else we do, will go to our YouTube channel. So if you want to check it out in 3 weeks or 3 years, you can head right there and do just that. This month has been our Epic Space Month, too. We've had NASA engineers of all stripes. In the next week, we've got asteroid hunters, Mars scientists, engineers, and more. There's so much to discover on that YouTube channel, so please do keep the learning going. Now, before I dive in with today's speaker, who I'm very excited about, I want to note we have a Kahoot for you. So if you want to join in with a little 4-question quiz between our talk and our Q&A, you can pull up that game pin below and have a little bit of fun with us for bragging rights at the halfway point of the show. Now, without further ado, I'm so excited to welcome in Connor Humphries, who is a researcher joining us from York University in Toronto, talking today about space junk. Now, this is a topic that we've actually had a lot of our teachers over the years say they wanted to learn a little bit more about. And so we didn't want to keep you waiting any longer. We wanted to bring in Connor to blow your minds and have a little bit of fun. And so without further ado, Connor, welcome to the program. Thanks for joining us and exploring by the seat of your pants, man.
Yeah, thank you. Thank you. I'm excited to be here, chat about what I'm researching. I wouldn't be, if I wasn't researching it, I wouldn't be excited about it. Like you always want to be excited about what you're looking into more and more
It's
often.
a pretty cool topic, and we have the luxury in this broadcast of bringing in some people that are like the absolute upper echelon of passion for absolutely everything they do. So I'm excited to learn a little bit more from you. I know you've got a lot to share with us. So if you want to bring up your presentation and dive in, let's do this thing, man.
Yeah, let me get this all nice and set up. We'll get our screen going. We get our nice second screen up and running, a little preview of the slides to come, and we'll get started with
Perfect.
beginning. Display settings, swap the sides.
And we're golden. We're off to the races. Thanks, man, and take us away.
Alrighty, awesome. So yeah, I'm Connor Humphries. I am the speaker today. I am a researcher in the space engineering field and the nanosatellite research laboratory run by Professor Regina Lee at the Lassonde School of Engineering, York University in Toronto, Ontario, Canada. And so my sort of story getting into this field is legitimately going from the ground up. I started from going into plant health science, construction, and landscaping, into sustainable energy and building technologies, so looking into cities, and then into environmental studies and sciences, before then ending up into the field of space. So I've looked legitimately from the ground up in terms of sustainability. And it wasn't until I was reading a Japanese graphic manga called Planets that I was introduced into the idea of sustainability in the space environment, and that is space debris. It introduced the concept that as we develop into any sort of field, be that, imagine plastics and the plastic waste that we generate that we're now recycling. Think of different explorations that we've done and sort of leaving little items behind. And so it introduced the idea of the Kessler syndrome, where we put up satellites, we do space exploration, and we sort of leave too many objects in space where they start colliding and creating debris. And if you create too much, it becomes difficult to explore space in and of itself. And so before talking about space debris as a whole, I feel I need to sort of build us up, just like my path, from the ground up, to understand the problem and the solutions that we're going for it. We need to start off with what is a satellite as a whole. There are natural satellites and there are man-made satellites. Satellites essentially mean any object that is orbiting just another object or body in space. And so the moon is a natural satellite of the Earth. The Earth is a natural satellite of the sun. The International Space Station is a natural or man-made satellite of the Earth. And I believe there was a speaker on recently for the Europa Clipper mission. That will be a man-made satellite of Jupiter in the not too distant future. And so man-made satellites tend to carry a bunch of different tools and instruments on them to complete a certain purpose. You can have scientific tools, such as CloudSat. We have a nice imagery here of a bunch of different satellites. These are all Earth observation satellites. They're all doing scientific analysis of the atmosphere, of the oceans, of crop health, plant health, forests, polar ice caps, so on and so forth. There's communication systems that are aboard these. People may have heard of SpaceX and Starlink and their constellation of satellites where they're all intercommunicating with each other to provide high-speed internet to people globally. And so these satellites all allow us to either understand more about the Earth, communicate with people all around the globe, or to even do deep space exploration and lunar observations. And so satellites are important and intrinsic to what we want to do and what we're moving forward towards at just in general as a population. And so they come in all different shapes and sizes. We have Grace, which is sort of like a trapezoid. We have Source, which is like a hexagonal structure, CloudSat, which is a cube, or Starlink, which is this nice isolated satellite on the right-hand side of the image, which looks like a shark fin, and they all weigh different weights. And that is sort of how we end up classifying satellites. It's by weight or mass. And so this is from Allen Space, just classifying the different masses of satellites. And they're categorized by that because the most important thing with space travel is how much fuel am I going to use to go from Earth to space or wherever my mission is taking me in space. And so it's always classifications by mass. And this is where the Nanosatellite Research Laboratory comes in. Nano is around 1 to 10 kilograms or 2.2 to 22 pounds. And you have Starlink, which is 1 to 500 kilograms or 220 to 1100 pounds. And you can go larger and larger. You can see CloudSat on there as well. And so satellites are undergoing a sort of revolution in how they're developed. In the past, just like with computers, you have those big bulky supercomputers that used to take up an entire room, and now they fit either onto our watches or with our cell phones or with our laptops. And similar things are happening with satellites where we can shrink smaller and smaller and smaller. And so instead of these large scale missions that are taking, say, 10 years to develop, where now our tools are a little bit out of date, we can produce a CubeSat, which is significantly smaller, in about 8 months. The lifespan of that satellite might be anywhere from 6 months to 2 years compared to a large scale mission for 10 to 15 years. But this downsizing has allowed universities and startup companies to start deploying satellites of their own. We can rapidly develop and deploy a satellite to monitor wildfires more regularly. We can test different scientific instruments more readily. And so we can build satellites a whole heck of a lot faster and a lot smaller. And even Starlink, with its mini scale size, is deploying a heck of a lot of satellites now. And so this allows me to show off what my lab has done in the past with our sonar missions. In the middle, we have I believe that's our Sonar 2, which is a 3U cube satellite. The U's are the units, just as shown before on this slide here, 10 centimeters by 10 centimeters by 10 centimeters. And our entire lab's purpose at the moment is related to sort of detection and tracking of satellites of other space debris that exist. And so our 3U CubeSat was put onto the gondola in the left image, and that gondola there is about the size of a minivan, all to take images such as seen on the right. That was taken from the ground, not on that gondola just yet. And that may or may not actually be a piece of space debris. It might be an airplane. But we will have images from the missions that occurred from my lab in future slides. And so this is the stratospheric balloon mission in and of itself. And so the gondola, I'll see if my mouse can come on screen. The gondola is down here, and that's the size of a minivan. So you can see the scale of the balloon it's attached to, which is then taking it up into the stratosphere afterwards. These scales are pretty huge in terms of what takes us to the edge of space. And the edge of space in this case is about 40 kilometers into the atmosphere as a whole. So we'll just skip ahead just a little bit into the video as it launches off. And so we were taking images of space debris and space objects from this stratospheric balloon mission. So I hope we've started to get an understanding of, okay, what are satellites? Why do we need to be in space? scientific missions, monitoring our environment, monitoring the Earth, communications, global communication with everybody. It assists us in every single avenue of our lives at the moment. And so the next topic is, of course, how many satellites really are there? Like, space is big. Earth is rather humongous. If you look out your window, you will never end up finding, the end of the Earth or seeing another country outside of your window. It is absolutely massive. And so this is from AGI, ANSYS Government Initiatives, and they did a simulation showing off all satellites from 2017 to 2027, or planned new satellites. And I'll skip ahead just so that we're a little bit closer to modern day. And so these numbers are actually a little bit dated. They, throughout this entire process, simulated 57,000 satellites. For context, there are currently about 13,000 active satellites in low Earth orbit around Earth. Starlink has about 6,400 active satellites. Starlink wants to plan for 34,000 satellites in its, constant communication constellations. Amazon has their own Cooper project, which is another 3,000 satellites. There's OneWeb, which is, I believe, 650. Canadian company Telesat, around 250 satellites of their own. Other countries, such as China, they have their 1,000 Sails constellation, which is planned to be 10,000 satellites. And there's two other companies that are planning another 10,000. And so we're really building up the amount of satellites that exist. So instead of 57,000 satellites, we can think along the terms of 100,000 satellites. And so I believe there's one more year to show off in this simulation. But you can take all of these dots and we'll be able to double them for the amount of satellites that are actually planned to be in low Earth orbit. There we go. There's our 2027 edition. And so all of these dots, we can double that in scale. The International Telecommunication Union, which, if you've ever listened to satellite radio and another person with satellite radio has, say, pulled up beside you in a car and you start mixing frequencies, you're hearing their radio, you're hearing theirs. That's what the International Telecommunication Union does for all of these satellite missions. They say, hey, you can use only a certain radio frequency band for communication. And so they've been filed for 1 million satellites, but we're saying 100,000 is the actual prediction for the future. And so there are a lot of satellites in general, and we can track a lot of them. Like Starlink has this image, or a lot of live maps, that show where Starlink satellites are, where they're going to be. If you put in your geographic location, such as this nice little person over here, it will tell you when a Starlink satellite will be overhead, which one will be in communication with you. And these red lines showing where Starlink is going to be and where it will go is a good representation of the errors that come up with having more low Earth orbit satellites in orbit around Earth. This is from an observatory down in Chile doing ground-based just telescope observations of space, and all of the streaks are Starlink satellites. If you're ever walking down the street on a sunny day and a car is passing by, you'll have that glint shine into your eye. This is exactly what's happening with these ground-based observatories and these constellations of satellites that are going up. And so now we can start to enter into space situational awareness, what my lab specializes in terms of detection and tracking, characterizing or identifying, okay, what is this thing that I'm looking at, predicting where objects will be, avoiding them, not so much my lab specialty, and then the really cool cleanup missions that are just starting to occur in the space field. And so again, we have a lot of satellites, but space is big. Earth is still big. Orbit around Earth should still be big. But we can see with that one gigantic blue line, a lot of the satellites are going into one sort of orbit around the Earth within that 500 to 7 kilometer sort of height above the Earth. And so altitudes or heights are sort of our roads, our super highways. And so if you put out your fist and you just start drawing circles around your fist, you'll start to notice no matter what you're doing, those circles are going to start, interacting with each other at certain points. And so if you're at the same height every single time, you'll see these crisscrosses, such as with the highways. And the reason that this occurs is for communication purposes. All of these constellations that are going up, they want to minimize internet lag. Nobody enjoys having slow internet. And so in the past, a lot of this internet was sent to geostationary orbit, which is like 35,000 kilometers out, an insane distance compared to only 500 kilometers above the surface of the Earth. And so everybody is fighting for those close altitudes. And if you've ever been on a long highway drive, you'll notice pieces of junk just off to the sides of you on the sides of the highway. With our orbits, those aren't just stationary. Those are now moving with you. The entire highway is moving. The debris is moving with you. It's moving across from you, from the sides, and it might even be coming towards you from the opposite direction. It might be coming from above. It might be coming from below. And so every satellite and every piece of debris is moving along with you. There we go. And so one might be wondering, okay, how often do collisions actually occur? And this is from AGI, again, a simulation from 2009. A Cosmos Iridium satellite ended up colliding. And this is when we had half the amount of satellites in low Earth orbit than we currently do. And so not only do they end up colliding, but they end up creating debris. They end up creating around 3,000 pieces of trackable debris. Again, not to scale as they show in the image, but this debris continues onwards. And there's thousands more of untrackable pieces of debris, as we can only see things about 10 centimeters in diameter or so. But this debris, at the height that it was at, can survive in orbit for potentially 100 years, if not more. And it will slowly start to come down from that altitude it was at, from 800 kilometers to 700, 600, to that sweet spot of 500 or so kilometers, where a lot of our new satellites and constellations are going. And so this is a little taste of where the debris aspect starts to come in. And so we know there's 13,000 active satellites. There is a plan for 100,000 more, but how much debris is there with all of these objects? So from the European Space Agency, there are 40,000 pieces of debris greater than 10 centimeters in scale. There's over 100,000 pieces of debris in 1 centimeter of scale, and 130 million pieces of debris 1 millimeter in scale and larger. And so one might think, okay, 1 millimeter, what does that really do? You can think of the tip of your pencil, that little piece of graphene, going around at such speeds that when it collides with a solar panel or solar array, as with this satellite here, Sentinel-1A, it leaves a 40 centimeter dent, or a dent that's the size of 2 soccer balls side by side. And so these satellites and these debris, they're not moving at kilometers per hour or miles per hour like a vehicle. They're moving at kilometers per second or miles per second. And so there is a lot of energy that all of these pieces of debris can impart on a satellite. And so what do we do? This is space situational awareness. We need to be able to detect and track these objects. And so one method of detecting them is using radar. If anybody has ever looked into bats and their echolocation, they send out sound waves, which then bounce off an object and go back into their 2 receivers or their ears. And we can do something similar, but instead of sound, we're using radio waves, electromagnetic radiation. We use radio waves, which then bounce off an object and come back to our receivers. The more receivers that we have, just like the bat's 2 ears, the size, how fast they're moving, their location, so on and so forth. We have ground-based optical detection. So these are your good old telescopes, such as down in Chile. And this is an image taken by Slingshot Aerospace of that 1,000 Sails constellation. They launched, they got their 18 satellites out, but unfortunately their rocket, after having successfully deployed the satellites, ended up shattering in and of itself. And so we have more rocketary debris. And this was from this past summer. And so ground-based detection does have its limitations. If it's cloudy, you can't see space. If there's a bunch of light pollution from cities, there you can't get the best detection. Starlink satellites and other constellations can make detection a little difficult. And so this grainy sort of image here is a world's first from a Canadian satellite, NEOSat, where instead of ground-based observations, we go for in-space observations. And so this is a picture of 3 satellites, RCM satellites from the Canadian government, used to calibrate satellites as observation satellites as well as ground-based telescopes. And this is where the lab's research sort of comes in. You might think, oh, we're in space. There's not really much that's going to make a lot of noise. Images will be super clear. And not so much. It's a little surprising. You can get a bunch of lens flare or glare where the image is a lot brighter than you would anticipate. There is still dust in space, something called zodiac glow. There is glow from the Earth's atmosphere that can make images a little bit brighter as well. There's other anomalies, as we can see in the bottom right here, that happens with some of these images. And so the idea with our lab a lot of the time is how can we use low resolution images, such as with star trackers, to detect these objects that we know where they are. And so one idea is we can flow images through computer algorithms, make them a whole heck of a lot cleaner in multiple stages here. And then if you've ever laid down on your back looking up at the night sky and staring at the stars, you'll see that the stars don't really move. But if a plane were to fly overhead, that plane would be moving. And so that's sort of the idea with the 3-frame resonant space object detection or association, is that these objects, they're going to be moving a whole heck of a lot faster than the stars that we're looking at. And so this is from one of our sonar missions. And you might see some objects moving here compared to the background stars. And I'll make it a little bit easier for everybody, where I've highlighted just a couple of the moving objects here. And so you might be able to see 3, 5, maybe 8 moving objects. And this is where coding really comes into play, because it's not just 5 or 8 objects, but really there were 25 objects in that display that we had. And so the last thing for tracking and detecting is satellite laser ranging. This is where geometry really comes into play. Learn your triangles, learn your angles, learn your triangular pyramids. That gives you distance to an object, that can give you its velocity or speed, and a lot more information on how that object is moving. So the next is identifying what the object is, characterizing it. From this nice little National Geographic GIF, we can see how the satellite is unfolding. You can see a lot of glare or glints coming off the solar panels, maybe compared to the base. And so this is work that Rhonda, a PhD student, is working on. She's looking to make an algorithm that can actually just take in a light curve analysis of these glints. If it's glinting slowly, then it's probably a stable satellite. If it's tumbling a lot, you'll have a lot of that reflection coming off of the solar panels. That'll be a tumbling satellite. And the rocket body, based on its material and shape, it will have a different light curve in and of itself. You can get further information based on the kind of light that it's reflecting, but that is more going into the nitty-gritty of characterization and details. But this is light curve analysis is how we would go about characterizing a lot of the space debris that exists. Next is predictions. This is the math that one learns when going into the field of space and space engineering as a whole that allows us to make these pretty simulations. You have the orbital parameters that allow us to create these simulations, and a lot more, such as satellite catalog ID numbers and more. So stay in school, continue with your math, continue with your science. And these are the items that become extremely important.
It gives me heart palpitations, Connor, just looking at it.
Yep. That's what we do when we're getting into the field. And so the next is avoidance, of course. You don't want your satellite to be hit, such as what happened with Iridium and Cosmos. And so there's 2 different ways that you can go about that. One is shielding. That is a Whipple shield that is shown off. Imagine someone is throwing a rock at you. That would hurt. The Whipple shield will take that rock and it will sort of collapse it and turn it into a bunch of grains of sand. Still annoying, mind you, but being hit by a bunch of sand will hurt a lot less than a gigantic rock. And so that is a trade-off of mass. You will be heavier, and everything in space is all about mass. You want to be as light as possible, otherwise it costs more and it's more fuel. The other way is avoiding these collisions, which is the trade-off of you need to calculate a lot. With that complicated math that we had before, you have to use your precious fuel to move out of the way. And when you're doing that, you might have to turn off your scientific instruments. And so it's also a function of time. And so there is always trade-offs with avoidance. And if you don't avoid, we get the wonderful collisions. And collisions, of course, create more debris. More debris creates more collisions. More collisions creates more debris. And that is, of course, the idea behind the Kessler syndrome. And so how do we stop all of this? These are world first missions that are happening. We now have cleanup missions that are occurring, will be occurring, will continue to occur. And this is what I'm really excited for in and of myself. We have what happened this past summer with the ADRAS-J mission. This is Astroscale and JAXA, or Japan's version of NASA, more or less. This is the very first rendezvous with a piece of space debris that has ever happened. And so this is a time lapse. They have more videos on their YouTube channel of this same time lapse. But this is a rocket body, I believe from the early 2000s, sent up by Japan. And so this is the first ever imagery captured of rendezvousing with a piece of uncooperative space debris. And as we rotate around, you can think of characterization, the glints that would come off of this rocket body. And you can even start thinking, how might we start to deorbit an object like this? But yeah, that is the world's first ever, and it happened this past summer in 2024. And the next large-scale mission is Clear Space 1, happening in 2025. This is a Swiss-based company that is paired with the UK Space Agency as well as the European Space Agency. They are looking to send up their own satellite that is going to rendezvous, clamp on to another piece of space debris, and they will actually look to deorbit it into the ocean. And so this will be a world's first when it comes to removing larger pieces of space debris. And so we are getting practice with deorbiting as a whole, as we aren't too used to actually doing it. This past summer, it's this summer, it's next summer, future missions occurring. The European Space Agency deorbited their SALSA satellite that was launched in the early 2000s, and they predicted where it was going to come back down, and they flew a plane right beside it to get more information on how it would break up in the Earth's atmosphere, drag, and a bunch of other information regarding it. And so space as a whole is turning from a place where we send things into space, they do their part, and maybe they stick around. We're looking to have a zero debris sort of charter put out where everything will look to deorbit itself at the end of its lifespan. We have a bunch of missions going on. Clear Space 1, such as in the top left corner, Astroscale's Cosmic 1 mission, which it will look to deorbit instead of just take pictures of debris occurring. You have, in the United States, NASA having just funded, this past summer once again, Starfish Space for rendezvous missions to refuel as well as deorbit satellites. And of course, I believe in 2026, 2027, we have humankind going back to the moon for the first time in about 50 odd years with the Artemis missions and future lunar gateway missions. And so there are a bunch of activities and games that students can do of all ages, from middle school all the way up to high school, university, so on and so forth. There's games you can play, such as Space Protector, which is the upcoming mission of Astroscale, NASA, Canadian Space Agency, European Space Agency. There's so many avenues to get in. You even have Mars missions that are coming up into the future. And so I'd just like to thank everybody that has assisted me from my own lab, showing off their research, providing images as well as videos. And if you want to learn more information about the lab that I work in, the name and information are there. But I hope everybody is extremely excited and interested in what is going on in space. It is no longer just sort of throwing things up there. We are looking to take care of the entire space environment and space atmosphere. So as we go to the moon and back, I am hoping to be that wonderful space trash man that is ensuring that we can continue to go into space safely and in a fun and exciting manner.
Nice. No better message than that. And yeah, honestly, like it is. It's the most exciting time to be ever interested in space. For our students in grade 3, 6, 9, we've got kids from all over today. Like when we were kids, there was 1/20th what there is going on as what you guys get to grow up with. You can literally go right now and look at robots on other worlds. You can follow spacecraft going to moons of Jupiter. You can learn about space junk and how we're starting to clean it up like we talked about today. Like it is really a fantastic time to be keen on space. And you kids in the classes today, you're going to be the ones that are going to the moon, going to Mars, going and doing these explorations. So like, if you're keen on this, keep doing science, keep doing math, learn a lot, and you'll have the chance to be like Connor and be like our other explorers here at Exploring by the Seat of Your Pants. It's so, so cool. So Connor, thank you so, so much, man, for that deep dive into space junk. What we're going to do to start before we do our Q&A is we are going to play our Kahoot together. So for those who are new to Kahoot, the faster you answer, the more points you get. And Connor, you can help us out with some of these answers because these are things you covered during today's talk. But what our classes win is our everlasting respect. And so that's pretty cool. We are going to dive in and get us underway. Our Odessa school, Oak Hills Terrace, there's like half of San Antonio in today, which is awesome. Let's get underway and do this thing, Connor, and give us a few hints along the way.
All righty, let's see what we got.
Right. And then Odessa, we're coming to you for our first question when we do our Q&A. YouTubers, please feel free to chime in as well. All right, question 1. What are some of the things satellites do for us? We led in with this. Connor talked at the beginning. Do they allow for global connectivity and calls? Do they study the Earth to help us in all that we do? Do they study other planets and stars? Or all of the above? Connor, do you want to help anyone out a little bit?
Saying I'm pretty sure a lot of that sounds pretty important to me. So
anyone who's done a Kahoot with me before, if all of the above is an option, it is the answer. Really interesting. So we had a nice breakdown here. All the above is correct. Let's see what that does to our leaderboard. Fearless Urchin has our lead going into question 2. All right. Let's see. True or false? A little bit of an easier one. Not a few options. Satellites have collided before in real life. Now, we had some footage of this. We had some simulations illustrating this. What do we think? True or false? Oh, wow. Sorry,
we're speed running it.
Yeah, you didn't need to have anything. 100%. I literally never had it where the Kahoot ends 5 seconds in because everybody gets the right answer. That has never happened in like 500 of these. So way to go, guys. Yeah, 2009 is our main example of this that you talked about.
Yep.
Fantastic. So before most of our kids were born, which is alarming for me as a 32-year-old. All right, question 3 coming up. Let's bring it up. Another quiz. We've sent how many satellites around the Earth total? We are set to have how many satellites around the Earth total in the next few years. So we had that illustration earlier of all the satellites around the Earth. Is it 500, 1,000, 10,000, or roughly 100,000? It's a lot. It was crazy. It almost blocked out the Earth in the simulation, looking at how many satellites there were.
Numbers in space are always big.
They are always big, yes. So a few of you thought 10,000, but yeah, over 100. Like, it's wild how many satellites we have up there. It's why space junk is such an issue. It's why people like Connor are researching it to help make sure that we can continue to do epic space missions going into the future without the risk of collision. Now, speaking of risks, in our final Kahoot question, what are some of the issues associated with these things in space? What are we afraid of? Are we afraid of the risk of hitting and damaging spacecraft? It's more than one answer, by the way. It's not just one. Are we afraid of making astronomy more challenging for people on Earth? Are we afraid of each bit of space junk coming and wiping out people on the Earth like the dinosaurs? Or there's no risk at all? We're totally fine. This talk has meant nothing to you. What do we think? So a lot of you got A. It is B as well. We're worried about astronomy. If there's more satellites blocking our view, that is a challenge. But the big risk, which most of you got, was that things could hit our spacecraft. So we're worried about that, but we're taking a lot of action to try and solve it. So, Connor, they were on the ball, man. You did a great talk because we got mostly right answers.
Awesome.
Our winner for all the marbles, drum roll, dun, 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 and anyone who played, way to go. Cheerful Bobcat is our winner. Kudos to you. If you are Cheerful Bobcat, let us know who you are in the chat. And we're going to dive in with questions now. So our Odessa crew, grade 6s, if you want to come up and start with a question, Oak Hills Terrace, I'm going to come to you in a second. And YouTubers, please do chime in. But Ontario, you can kick us off. Hey, guys. Hi. Come on in. Do you have any questions for Connor? What do you think?
All righty.
You can talk. They can hear you.
Hi.
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 Hello.
Okay, what's your question, Olivia? You're too scared?
How many what's it called again? Satellites? How many satellites have like crashed together?
Ooh, good question.
Oh, that is a good question. So collisions themselves for satellites, I will say so far have been pretty rare. The main one was from 2009. There have been a lot more sort of anomalous things that have occurred with satellites that have led to breaking into fragments. And so that can be like miswiring that has happened, and they'll end up getting like an electrical buildup, which ends up shattering the satellite overall. Or there can be sort of silly little tests that happen when it comes to trying to interact with a satellite where the purpose was to try and destroy the satellite in and of the first place. And so some missions like that have occurred in the early 2000s.
Yeah. So I'm surprised it's been that few. Like, given how many satellites there are, I'm surprised that we've only had one real epic collision where they blew up and blew to smithereens. Like,
and
that
so
is,
it's one of those things where you can have, it's more so you'll have those smaller debris collisions, or you'll have those malfunctions that lead to, breaking apart and debris. But actual satellite on satellite, thankfully, has been rather limited to maybe a handful of cases so far.
You harped on something, and I want to make this really clear for kids. So something that's about the size, the tip of my pencil here, would make a collision that's like this big on a satellite, because they're going faster than a bullet. So when we fire a bullet from a rifle, that is going way slower than it takes to have satellites orbit the Earth, which means that really, really small things can have a really big impact. It's why this is such an issue. So I'm really glad we got that as our first question. Thanks, Olivia, for being willing to do that. Oak Hills Terrace, since there's like all of San Antonio in this classroom today, we'll do two questions with you guys back to back. YouTubers, you can chime in as well.
Sit down, Andre.
Come on up and ask a question. You get two in a row, okay?
Okay, tell me your name.
My name's Isla.
Hi, Isla.
Tell your question.
My question is, what is in space trash?
Ooh.
Okay. So in space debris or space trash, you'll end up finding, or we can think about it in the way of what makes up satellites a lot. And so that will be wiring, that will be the metal that makes up the frame of the satellites. There can be glass and plastics that are involved with it. Even something as small as like a paint fleck, which could be almost like a grain of sand in and of itself. All of that will be those projectile missiles whenever they break apart and are going at those high speeds. And so metals, plastics, wiring, anything else that makes up solar arrays, and other things that are on those satellites. Otherwise, there are natural pieces of debris. So little meteoroids, micrometeoroids, so little rocks, space dust. Those are what make up a lot of the debris.
Yeah, so everything that we blast up into space can theoretically turn into junk. Just like if you've got like a pool toy, sometimes it'll shed some paint, sometimes it'll shed some plastic. If I dropped this glass, it would be lots of little glass shards. And anything that we put up there can theoretically turn into space junk. And it's why this is such an important thing. So that's a great question, Isla. All right, we're going back to Oak Hills Terrace. YouTubers, feel free to chime in as well. I'll take one online question, and we'll go back to Odessa. We'll see if we can sneak in a few more together. And classes, please do write down additional questions. We'll get them to Connor after the broadcast. Okay.
This one's kind of a two-parter because they kind of are related. Okay. So, what was your question?
My question was, how do you know where like the stuff that you sent to space is gonna land?
And then her question was,
what happens if it hits the Earth?
so if there's space debris that comes down, then what happens? So how do you know where it is and what happens when it lands?
Great questions, girls.
Yeah. And so that goes a lot into those sort of prediction math that we have for creating our simulations. We have the orbital parameters, so we know how it's sort of traveling around. And if we have a good picture of where it's traveling around, once we want to sort of shift it to come back down into Earth's orbit, then, if you're ever riding a bicycle or anything like that, you'll feel the wind blowing against you. That's the atmosphere blowing against you. And so we start to account for that atmospheric drag and how that satellite will start to slow down and come back down into Earth. As in your orbit, technically everything is still falling towards the Earth, but it's going so fast that it's staying around the Earth. And so once it's in the atmosphere, it will just start to come down, 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 down. And so it's those same predictive simulations that we have accounting for that slowdown that will allow us to be like, okay, this is going to fall over, say, the Indian Ocean or the Pacific Ocean. And with that, a lot of that goes into what will happen when it comes back to Earth. And that depends on the mass or the size of the debris in and of itself. A strong majority of it's like anything that is within that 10 centimeter range, it's going to burn up in the Earth's atmosphere. The Earth in and of itself is probably the greatest incinerator for garbage that you could ever have and wish for. And so then...
Right? Like you highlighted that we actually do send things sometimes. We'll take a satellite, we'll like steer it towards the Earth so it'll just blow up in the atmosphere. Like
that's the future, yes. That's coming up in the next year. Larger pieces of debris, those will end up impacting the Earth, but with our aiming skills and our math and science, we have them hit the ocean compared to solid land. But no, when it comes to the actual size or scale of a lot of these objects, they don't end up doing all that much. It's not like what happened with the dinosaurs in any way, shape, or form. We are significantly smaller in that regard.
I want to harp on two things here, because I've done a meteorite talk myself, and it's worth noting, like 70% of the world is ocean, and most of the land on the Earth is uninhabited. So if you crash in Siberia or if you crash in the Pacific Ocean, there's no danger to a person, even from a fairly big thing the size of like a baseball. It's the really, really big things that we're kind of worried about, but most things don't fit that bill. So that's a really important note. And secondly, a lot of things hit the Earth every day. NASA estimates 48 tons of stuff a day hits the Earth. That's like 30 elephants a day land on Earth, but they're all tiny, tiny, tiny little things. So when you look up, if you see a shooting star, that's all that is. That's like a piece of space junk, or it's a meteorite that's burning up in our atmosphere and making that streak in the sky. So next time you see one of those, you can think of Connor's talk and all the cool stuff we're doing with space junk exploration. All right, time flies and you're having fun. I want to take a few more questions before we wrap up together. So grade 6 or Odessa crew, if you guys want to come back in and ask another one, you are good to go. Hey, come on. Oh.
Oh God.
Yeah.
Hi, I'm Ben, and wouldn't the space trash just burn up in the atmosphere before it hit Earth?
Yeah.
Absolutely, yes. So again, that goes back to the size of these things. So with that time-lapse video of that rocket body that was orbiting the Earth, that Address J mission, and those photos that were going around, that piece of debris is so large that even after going through the Earth's atmosphere, it would still make impact with the ground, with the ocean, wherever it ended up landing. And so, yes, the majority of it, absolutely. It's going to go into the incinerator that is Earth's atmosphere, and it will be burnt up, never have to worry about it. But then there's larger ones, which
yes,
you do need to account for.
We do, and that's why we need people like you doing this research. So, Connor, time flies and you're having fun. I want to make sure our classes have a big chance to say a thank you and farewell before they go. So is there any last message you want to leave us with about space junk before we say goodbye? And again, I'm going to get all our classes, all those resources you shared to keep the learning going, but wrap us up with one more note before we bring in the kids.
Well, I'd say that with the development and the future that we're going for, we are looking to be a lot more conscientious, just about our environment as a whole. when it comes to like plastic pollution, we're starting to clean that up and be a lot more aware of what we do. And so sustainability as a whole isn't just something for space, but we are definitely starting to apply it to the space environment. And so I hope that a lot of people have been interested with, even though space is really large, we need to keep our nearest atmosphere really clean to keep these space highways operational. We got those lunar missions, so we're going to have those lunar space highways that we need to make sure remain clean as well.
Connor, this has been so much fun. Thank you so much for joining us. For all the extra resources and more classes, please do check this out. Share it with your family and friends on YouTube. We really appreciate you sticking around today. And what we do to wrap up every broadcast, Connor, is I'm going to bring in our classes to say a big thank you and farewell. So Mr. Rottenstass, our equipment crew, YouTubers, thank you so much, everybody. Have a wonderful day. Bye for now, guys. See y'all soon.